Hi, my name is Alan, and I'm going to present our topic, which is optimization layers in deep learning. We are group 5, and the names in the group you can see Ahmed, Alan, Upangana, and Ian Song. Okay, so starting with the problem formulation. So basically, we have an optimization problem that is well defined by the argument of an objective function, which is f here. And this objective function has a decision variable, which is z. Uh, S is the feasible set. So z has the optimal z has to be in the feasible set. And y here is an input to the objective function, for example. So this is basically an external signal that enters to an optimization problem. So the focus of this presentation is to present works that compute the gradients through an optimization layer. So basically what we actually want is this partial derivative, which is the partial from z star, which is this argmin, the result of the solution of the optimization problem, with respect to this external sign or to a prediction of this external sign. That's why we put the hat in the y. So this has some deep learning applications. But it's important to compare traditional deep learning and deep learning with optimization layers. So traditional deep learning approaches are filled by neural networks that has differentiable layers all over the architecture. Um, However, sometimes the aim is to approximate some decisions that are outputs of structured optimization problems. So basically, in some applications, we are not interested in predictions, but we are interested in decisions that are outputs of optimization problems. So that's the reason that optimization layers inside deep learning frameworks are important. And it's very common that they have the optimization layers are the last layer of the architecture of a deep learning architecture. Um, this is because then the final output of the model is a decision variable, because the last layer is an optimization layer. As an example here, you can see, for example, like a data-driven decision-making example. You have an input. Okay, we have like some contextual features here as x. This contextual feature enters into traditional neural networks with all differentiable layers. And this neural network outputs a prediction, y hat. Okay, so this y hat is used to some types of optimization problems or some types of mathematical programming that solves the optimization problem to output a decision. Okay, in this case, Z star, we are assuming that this decision is optimal with respect to the prediction. And then, for example, we can put into the objective function with the actual y to evaluate or to create like a loss function which mimics exactly the downstream task. So this is a type of end-to-end learning, right? Because we are trying to directly minimize the objective function that we have from the optimization problem. The cool thing is that we can do, if we are able if we are able to make um, an optimization layer that is differentiable, then we can make a backpropagation through the whole architecture. So from the end task, which is the final objective function, through the optimization layer, and then through the neural networks. So that's the main point here. But then what are we actually learning in this whole framework? Well, we are actually learning the theta here, which are all the weights of the neural networks, because we don't have anything to learn in the optimization layer, because there is no parameter to learn. But it's important that this layer allows backpropagation in order to learn a neural, suited neural networks. So basically, you have like this chain rule, which is the partial from f to z star. Okay, so from f to z star, and then the middle one here, that is the partial of z star with respect to y hat. And this is the complicated thing that we are going to see some works that focus on this, which works on taking the gradients of this mathematical programming. And then the neural networks per se, which is basically well known as the partial of the prediction with respect to the weights of the neural networks. And then we update the theta, which are the in parameters based on this chain rule. But what are the implications of learning these thetas, right? Well, basically, once we learn the theta, we will learn this y hat. Not to have, it's not important that y hat mimic exactly the parameters that we want in the mathematical programming or in the optimization problem, but we want to find these predictions in such a way that we have an optimal value of the objective function in the end. So it's like a latent space that you adjust in such a way that you will have optimal decisions in the end, decisions that decreases your downstream or your objective function, or a cost function in this case, because you want to minimize. So yes, that's this is the implication of learning theta, because it seems, oh, we are just learning the weights of the neural networks. Yes, but we are learning in such a way that now we want the decisions to be optimal. So based on these motivation, applications, and problem formulation, we decided to propose 3 questions. So the first one is, what are the main characteristics that an objective function must have to allow differentiable layer through it? So in these proposed questions, we are going to see different types of optimization layers. We can advance that there is no general framework to deal with different types of optimization problems with only one framework. And this is actually one of the challenges that we are going to see in the next slides. Second question is, when or why is it beneficial to find gradients through the OP differentiable layers, instead to first find the predictions and then optimize the predicted problem? So we have seen this y hat. Basically, we could have like a pair of training data that is x and y, and we could learn y first, and then we would not need to have like a differentiable layer, because we just get the predicted y and solve the optimization problem to get the decision. But we will see that this is not so good in the next slides. Third is, what are the remedies to decrease the time consumption in training process of ANN, of the neural networks, with that of OP differentiable layers. So basically having OP differentiable layers increase the time consumptions, and we are going to see some remedies to decrease it. First, addressing the question one, which is basically a survey. The question one is basically a review of the literature. First, we start with a work that focuses on quadratic programming. So basically, quadratic programming are all the optimization problems that follows this specific formulation, which has a matrix here, which is Q, and a vector C. And in this case, the decision variable again is Z. So you want to minimize this objective function, and the constraints here has to be linear in the quadratic programming. So by formulating the OP like this, Amos and Coulter proposed the KKT, which is the Karush-Kuhn-Tucker conditions, differentiation. So basically, there is a way to solve quadratic programming formulations, which is solving the KKT conditions. So this work from 2017 proposed to differentiate the KKT conditions. Yes, so basically by differentiating the KKT conditions, you can find this partial of Z star with respect to the Y. So the differentiation are from the optimal decisions with respect to the quadratic parameters Q and C. And also, you can also differentiate through these inequalities, A and B. They also can depend on Y, for example. We didn't put here in the formulation, but it is also possible. So yes, basically, the thing is, all these matrices or vectors that depends on Y, they need to be differentiable to be inserted in this end-to-end learning frameworks. Okay, we also have words that deal with linear programming, but they are mainly approximations. The first one is they leverage the previous work, which is from the Amos and Coulter 2017, but they add a very small quadratic regularization term. So basically this Q here will be very, very small, as we put here as lambda I. By putting this, we assure that this is much smaller than this, and we have an approximation of a linear program. Linear program is basically C transpose times Z, subject to the same constraints as we had in the quadratic programming. So then, by formulating the OP like this, Wilder et al. 2019 proposed to solve linear programs with the same quadratic solver. So the approach is the same, taking the gradients through the KKT conditions. Other approaches deal with linear objective function, but they don't put restrictions on the constraints. So they are not linear programming necessarily. They actually contain linear programming set, but they are not only linear programming. They don't put a restriction on the constraints. So in this case, El-Mashtub 2017 proposed computing the gradients with a surrogate objective function. So the gradient computation is dependent on the optimal value of a predicted Y and the optimal value of a perturbed predicted Y. With this, note that the time to compute the gradient is dependent on the time of finding the optimal solution. because to solve the gradient, you need to compute two times the optimal value of something, which means that you need to call the solver twice in each iteration of the gradient approach, the stochastic gradient approach, for example. So this is not so promising, right? Because for each iteration of the optimization procedure, the whole optimization procedure of the framework, you need to call the solver twice, which means that if your problem is big, um, you will need to call the solver, and the solver will take time to solve this optimization problem once and twice and three times, and how many times you need your your neural networks to converge. And these we skip these details, but this also happens with the previous works, because in the previous works you also have to solve the KKT conditions for each iteration. So this takes a lot of time. Okay, basically we just summarized some of the works, but in general, we have these types of optimization problems that can be solved by that we can find some optimization layers. For example, convex quadratic programming we have seen, and they are an exact differentiation, so they are not approximations. Linear programming we have seen also, they are mainly approximations works. Linear objective function, they are also approximation works. Cone programming, exact works. DCP, exact differentiation. And dynamic programming is approximation. Okay, addressing question 2. So question 2, just to remember, is why combine everything in a framework if we could simply separate them, first predict y and then optimize it without the need of an optimization layer or optimization differentiable layer. Well, suppose you have a y here and then you solve an optimization problem, and then you have z star, which is the optimal decision variable based on this y here. Then you will have a result that is, like, for example, you put the result in the objective function and you evaluate it. Okay, this is first answer. Now, suppose you add a noise in this y, and we call this as a prediction. So we are making an error in a prediction with compared to the actual y. And then we do the same thing and we have a new result. These results can be very different, even though the error is small. Why? Because you don't know the sensitivity of the objective function or the optimization problem. If you change a little bit the input, it might happen that the difference in the output is extremely high. And that's the reason why we want to do end-to-end learning, because if we focus on the prediction of y itself, even though we could make these to be very, very small, maybe it's not small enough to have these close to each other. So end-to-end learning is an alternative. If predictions are not so accurate, we are very unlikely to have a control of the OP output given a prediction error. But having end-to-end approaches, we try to directly minimize the downstream task by aligning the loss function to the decision loss, to the downstream task. Okay, and let's see question 3 now. Question 3, just to remember, is the computation limitation. We remember it's very time consuming because in stochastic gradient descent approaches, for example, you have to call the solver in each iteration. Yes, so again, we have to call the solver to find optimal solutions in each iterations. Calling the solver in each iteration of the learning process is extremely time consuming, obviously. And for hard optimization problem, for example, OP layers become impractical, even if the differentiation is allowed, only because it takes a lot of time to solve it. So what are the remedies for the time consumption? So recent research directions are aligned to study warming up solvers to previous solutions that have been explored during the learning process. Other research directions is to use transfer learning from decoupled methods, which basically first learn the predictions of y separately without any optimization problem feedback. So first you do this decouple, and then you transfer the whatever you have learned to a combined formulation. So just continuing here, when the parameters is learned first without the help of the OPA formulation, yes, and then fine-tune the in parameters by incorporating the optimization layers. Another way is relaxing the solver is also a possibility, but this research still lacks all guarantees that the parameters will actually converge to reasonable parameters. Okay, so to end our presentation, we present a brief of the challenges. First, we already mentioned, well, actually, we mentioned both, but just to give some more focus, the first challenge is how can we make a general framework to encompass different types of optimization problems? Okay, it seems very utopic to think about that, but at least having um, uh, like an algorithm that even call the specific solver, because of course we will have to call different solvers, but even though if we are able to make the same steps every time, it would be nice because then we would have a general framework. But this is not the case now because each work or each optimization differentiable layer is very different from each other. Um, Computation limitation is also a problem. So basically, it's a problem that comes from two sources. First, the size of the optimization problem. So we cannot solve extremely big optimization problems that contains hundreds or thousands of decision variables. And also depends on the type of the OP. So if it's discrete OP, even with a few number of decision variables, it's impractical. So that leads to the end of this presentation, and thank you very much for your patience and to see the presentation till the end. Yes, bye bye.